Okay, everyone. This is probably one of my favorite sections of the course. It's a problem that I came up with myself, and so I'll explain it to you, and I'll give you help as we kind of go through some of it together, and I'll let you finish the rest of it. This is section 2.10, optimizing a trip upriver. And I'll tell you how I came up with the problem. I was in New Orleans at a math conference, and I was high up in a hotel looking down on the Mississippi River, and I noticed there was a tugboat that was pushing the barge up the river. So if this is the Mississippi River right here, and here's a barge that's being pushed by a tugboat, and it's being pushed up the river, and the current was going this way. So here was the current of the river going like this, and it was pushing the barge upstream against the current. And I got to thinking, I wonder what is the optimal speed to push that barge up the river. And as soon as you say optimal, you have to have something in mind. What is it you're trying to optimize? And so what I was thinking of is what's the most economical way, or basically the most energy efficient way, the way to do it with the least amount of energy or the least amount of work to get it upstream. And I realized that was an interesting question for a couple reasons. One is that I remember from high school physics that the work or the energy, I'll use both W and E here. What do I use in the book? I use E for energy. I'll just use E for energy, but it's the same thing as the work. The energy involved is equal to the force that you're exerting times the distance that you travel. Okay? So if you push something, down a sidewalk, and you are pushing with a certain force and you push it a certain distance, all you have to do are have the units of force and the units of distance, and you multiply those together, and you get the amount of energy that you expended in pushing it down the sidewalk. And so that's what we wanted to minimize. So I knew that. And the other thing I knew is that the same thing that we did in the previous example is that if the force that is involved in pushing that is just the force to counteract the friction with the water. That's what you're overcoming. So the force you're trying to overcome is the force due to friction. And since this is a fairly slow object that's being pushed through the water, we can assume that the force due to friction is just going to be proportional to the velocity, okay, to the speed. So in other words, if you're pushing it at twice the speed through the water, the force needed is going to be twice as great to push it that fast, okay? So those are the two fairly simple, straightforward things from physics, high school physics, or even junior high, probably high school physics, that you need in order to do this problem. So let's just start with that and go through and do some of this together. So the first thing is, given these two things, what's the amount? If you want to move this, let's take a simpler example. Let's say we're on a lake now. We're not on a river with a current, but instead we're on a lake, and in this lake we're going from here to here, and this is point 0 and this is point P, distance P. And so we want to just push it across this lake, a distance P, and the question is, what's the amount of energy that it'll take to do it? Well, let's do it. First of all, we see that the amount of work or the amount of energy, I'll use those two words interchangeably. The amount of energy is going to be the force, and this is the force needed right there, times the distance. And in this case, the distance from 0 to P is just going to be P. Right? There's the distance that you travel. So there's the amount of energy that it's going to take to cross this lake. See that? Okay. And so I think one of the first questions I ask is, what's the minimum amount of energy? What's the minimum amount of energy it would take to cross that lake? If you really wanted to minimize things, how could you do it? What would be the strategy? And let me see if I can get a little more light on myself here. I don't want to have glare spots on the board, but yeah, that makes it a little bit better. And so let's think about it. Here's the energy. Notice it's K times V times P. P we can't do anything about. That's the distance across the lake. That's determined. Okay. K is some sort of constant. Okay, so that that depends on the shape of the object and things like that. So that's set. The only thing we have choice of is what's the speed that we're going to push it at. And notice that you're multiplying these three things together, and so as V gets smaller and smaller, the total energy needed is going to get smaller and smaller. See that? So basically, however small you want the energy to be, I can get it that small just by choosing V to be small enough. I'd have to know what P and K are, but once I know what P and K are, whatever you want this to be, I can get it that small by choosing V small enough. So that's kind of interesting. So if you're crossing a lake, let's stick with the lake here for a moment. Then the amount of energy it would take, you could be as small as possible. 0 would be your minimum. You never quite hit it, but you can get as close to it as you want. Okay, so then the next question I ask is, why isn't that realistic? If you had a barge, a tugboat that was pushing a barge across the lake, why would they not push it infinitely slowly, just barely going across? And of course the answer is that by the time you cross, the barge would be rusted, right? It'd take 100,000 years, and no way are you going to do that. So a more realistic thing takes time into account, right? You don't want to take an infinite amount of time or centuries in order to cross the lake. You got to pay your employees, and you got to get the whatever this material is, you got to get it over there in some amount of time and things like that. So then I got thinking, okay, so if you're in charge of a company that wants to move it across this lake, what you really want to minimize is not the energy. You really want to minimize the cost. Okay, so I'm going to let C stand for cost, and I'm not going to write all this stuff down because it's all in the textbook. And so just to save space, I'll just leave it. Doggone it! I'll just say C is equal to cost. Okay, so the C is the cost. I got a little spot up there. Okay, so then I thought, okay, so what are the things that's what you're really trying to, if you're a company, you're trying to minimize that. What are the things that are involved in the cost of moving this thing across the lake? Okay, and again, I'll answer my own questions here. I wish that we had some good interaction here, but I challenge you, go ahead and turn this thing off and think about it before you get my answer. But I thought, well, okay, there's two things involved with the cost. The first thing is the energy, right? You're paying for the gas, and so you want to minimize the amount of gas it's going to take, fuel oil or whatever, diesel fuel, to go across. So one thing is the energy that's involved in crossing the lake, and so that's part of it. So the cost is going to be some constant times that. I'll use the same things. Okay, some constant, I'll use a little alpha there. So what's alpha going to depend on? Going to depend on what? The cost of the fuel, how efficient your engines are, things like that. That's all going to depend. That's all going to determine how much the cost of the energy is. And then the other thing that you're having to spend money on if you own this company is you're paying the employees, right? You have maybe a couple people on board there, or at least one. And you're interested in that person's time, and you're going to have to pay for that person's time. And so beta, T stands for time, and so you want that to be as small as possible. I mean, somehow as small as possible as well. And what's beta going to depend on? What's that? That's kind of the hourly rate you're paying them and how many people, if you have one person on there versus 3 people and so on, okay? So there's what you're really trying to minimize if you cross the lake. And so now you can write a function of the velocity to see once what's the cost that it's going to take to cross a lake, given that you are going at speed or velocity. I'll use those two words interchangeably as well. Velocity v. So what is it going to be? First of all, we already have the energy. The energy is right there. KVP. Now we have to add the cost of the time. So that's going to be beta times the time. But see, we want to get everything in terms of just one variable here. If I put t here, we would have two variables. We'd have, well, what's the time it takes to cross the lake, and what's the velocity that you're crossing the lake. We want just one variable there, okay? All these constants are just set, but we want just one variable for crossing the lake. So the question is, how can I get time in terms of velocity? And hopefully you know that. You know maybe from junior high math or something that distance is equal to rate times time, right? If you go at 20 miles an hour for 3 hours, you're going to go 60 miles, right? So distance is rate times time, which means that time is equal to the distance, which in this case is p, divided by the rate, which in this case is v, right? If the distance that you're going is 10 miles and you're going at 5 miles an hour, 10 divided by 5 miles an hour, you're going to spend 2 hours making the trip. Agreed? So this thing right here is going to be P over V. So there is a function of just one variable, V. And so we want to know what's the choice of V, which is going to minimize the cost in going from here to here. Okay? And that minimum cost is going to depend on the values of alpha and beta, and it might also depend on p, hard to say, and also k. It's going to depend on probably all those things. And so so how do you find the minimum value? So I'm going to not do too much more on this, except to remind you from Calculus 1 that if you want to know when a function takes on a minimum or a maximum, you need to know where the slope is 0. And the slope is 0 means that the derivative is 0, right? So back from Calc 1, you need to do what? Take the derivative of this thing, set it equal to 0. I'll just again get you started here. Take the derivative equals all this stuff, set it equal to 0, and then solve for v and find out what v is. What's the value of v, which gives you that minimum. Minimum cost. Okay, so there's that one. Okay, so let you finish that. Now let's go back to the river. Okay, let's go back to the river. So the difference between the river and the lake is that this river has a current to it. And so let's let V sub c stand for the velocity of the current. And notice the velocity is going to be positive in this direction. So if it's 3 miles an hour, that means it's 3 miles an hour against the direction that you're trying to move. Okay? So we've got the same sort of situation. We want to minimize the, let's first try to minimize the energy. So we want to go from 0 to P. Here's 0 right there, and we want to push this thing up river to P. And so we want an expression for the amount of energy it's going to take to get from here to here. Okay? So let's think about it. The energy is going to be the force. So here's the force. There's the force that you are exerting all the while that you're pushing this thing through the water. And now we have to multiply that by the distance. But this is where things get a little more subtle, because I'm not interested in this distance. I'm interested in what's the amount of water that I'm actually pushing this thing through. What's the distance of water that I'm pushing this thing through, right? That's what I'm after. And so I call this the effective distance. Basically, what's the distance that you are really pushing it through the water? If you started right here and there was a little leaf in the water right there by you, and by the time you push the barge up here, where's that leaf that you started with? That's not there anymore. That's way downstream, right? You started right there with a leaf, and you are now upstream, but that leaf is way downstream. So that's how much water you actually pushed through, right? So your effective distance is what we want. Okay? And this is the hardest part of this problem for students. I know from having taught it for years. And so I have a little note down at the bottom of your page there, on page 35 of your textbook. I say, to understand effective distance, think of it this way. Suppose that for a daily workout, you cross a lake, which is 12 miles. So let's go back to the lake again. Here's a lake, which is 12 miles. And you're kayaking on it, and you're going at 6 miles per hour, which is a pretty hefty speed. I think I can do that short term, at least in a kayak, but that's pretty fast, okay? 6 miles an hour in a kayak. So then, how much time would it take you to do it? Do you agree that the amount of time, if you're going 12 miles and you go at 6 miles an hour, the amount of time is going to be 2 hours, right? It's going to be 2 hours. But now, suppose one day that you go to do your daily workout, the lake is not unavailable. Okay, they just put some chemical in it to kill all the algae or something like that. So you can't be in there, and so instead you go to the local river. And so the local river, I'm just following again the example that I gave you, has a current which is 2 miles an hour going this way. So the current, V sub C, is equal to 2. So there's the current. And you do the same thing. You start right here, and you start at 0, and you go 12 miles upstream. You kayak 12 miles upstream, and you still go at the same rate that you always go. When I say you go at the same rate, I mean you just put your head down and you just paddle at the same rate that you always paddled, okay? You've got that paddle rate down. And so the point is, here, you were going 6 miles an hour through the water. Here, you're also going to be going 6 miles an hour through the water. Agreed? If you were in the water here and you saw a little leaf there on the water, you'd be going past it at 6 miles an hour. Here, the same thing. You're right there, and a little leaf that's in the water right there, you're going by it at 6 miles an hour. So you've got your head down. You can basically forget about the fact that you're in a river. You're just doing the same thing you always did. You're going 6 miles an hour through the water. Okay, so let's let V be the same thing as before. That's 6. That's your speed through the water. So we have to be more careful here. That's your speed, or that's your velocity through the water. Okay? But the question is, how fast are you actually going along the bank? In other words, if someone here on this shore of this lake were to follow you, they would have to jog at 6 miles an hour in order to follow you. Here, if someone was following you, how fast would they have to jog? You're going 6 miles an hour through the water, same as you were here, but the current is coming backwards at 2 miles an hour, right? So do you agree that your speed through the water is now going to be 6 minus 2, which is 4 miles an hour. Agreed? You're now along the beach, you're only along the shore, you're only going at a rate of 4 miles an hour. So if you go a full 12 miles along this shore, just the way you did 12 miles along this shore, you're going at what's your effective distance is the question. What's your effective distance? First of all, notice that you are going from here to here, which is 12 miles, and you're going at a rate of 4 miles an hour. So do you agree that you are 3 hours in the water? 3 hours in the water. So you're in the water for 3 hours, and all 3 hours that you're in the water, you are still pushing through the water at that speed. Agreed? You're still pushing through the water at this speed. So your effective distance, the amount of water that you've passed, this is the speed with which you're going through the water, 6, and you're in the water for 3 hours, and so your effective distance is 18 miles. Okay, in other words, the workout that you did this day, in which you went 12 miles upstream, if you would have done that in a lake, you would have gone 18 miles in the lake, because here you were going against the current. Okay? So, let's think about what we did here. How did we figure out the effective distance? The first thing we did was we had to find out how much time it took to get from here to here. And so the amount of time it took to get from here to here was what? It was 12 divided by 6 minus 2. Right? There's your distance. There's the rate at which you're going along the bank. So 12 over 6 minus 2, 12 over 4, that's what gave us our 3. So the same thing is going to be here. Our distance that we're going is P, and the rate at which we are going through the water, this was 6 minus 2, this is going to be what? V, there's your speed through the water, minus the speed of the current, which is Vc. So there's your distance. There's the rate with which you're going along the bank. Right there, you take the distance along the bank divided by the rate at which you're going along the bank, and there's how much time you're in the water. Okay, so there's your time, and now once you have your time, you have to multiply that time by the speed that you're going through the water that whole time. And what speed are you going through the water? The v is your velocity through the water. You're going to multiply that by v. Okay, so there's your speed through the water. Speed through water. Okay, I have to draw kind of small there. Okay, so there you go. That's the hardest part of this problem. Make sure you understand that, because it's a really interesting problem, but you need to understand that point. And so now we've got a formula. The amount of energy it's going to take in order to get from here to here is going to be kV. That's the force, times your effective distance. And your effective distance is going to be your speed times the time. And your speed is v, and the amount of time is p divided by v minus vc. And so notice if you multiply that all out, you can just write it as k p v squared. I like to pull all the constants together. kpv squared, all divided by v minus vc. So there's the energy that it's going to take in order to get from here to here. And the same sort of situation as before, you want to find out when will that energy be a minimum. And so what do? In order to find out where the energy is a minimum, you need to find out where the derivative is 0 and solve it for velocity. So I'll let you go ahead and do that. It's going to it means using the quotient rule. Your variable is v, so there you have a v squared, there you have a v. All these other things are just constants. So it's like if I had 7v squared over v, or let me write it in terms of x since you're using x's. If I had 7x squared over x minus 5, for example. How would you take the derivative of that? Here you do it the same way. You've got a constant times the variable squared, all divided by the constant, all divided by the variable minus the constant. So go make sure you know how to do that. Okay. So anyway, you will find the optimal speed with which you should go upriver. And that's really cool because it applies not only to kayaks, but it would apply to swimming, it would apply to canoeing, it would apply to boating, it would apply to pushing a barge up the river. Whenever you want to go up a river, if you're going up a river and you want to do it in the minimum amount of energy, minimum amount of work, then whatever you get here as an answer, that's going to be your result. And your answer is going to be just in terms of the current. Okay, it's going to be something just involving the speed of the current. Okay, so see once what you can get. Okay, so that's that part. Then the next thing, this is problem Roman numeral 4 now. Roman numeral 4 says, well, let's go back to cost again. Okay, let's go back to cost. What if now we want to go from here to here, and we have this barge, but now we want to minimize not the energy but the cost. So we do it kind of the same way as before. We'd have cost, and this is all going to be in terms of velocity again. It's going to be some constant times the energy plus some constant times the time, right? The cost involved in getting it from here to here involves both the amount of energy that it takes to do it plus the amount of time it takes to do it. So how would you finish that? All of this stuff can go right in there for energy. That's all there. And the time, that's going to be the same as before, isn't it? Your time is going to be, well, let's think about it. What's the time going to be? The time is going to be the distance. Well, I'll let you figure that out. Okay, you figure out how much time is it going to take to get from here to here. Okay, it's same sort of idea as we did before, but you've got to come up with an expression here which involves v, something that involves v, and that's going to stand for the time it takes to get from here to here. So that goes in here, and you've got this, and then same as before, you want to minimize it. So you take the derivative, set it equal to 0, and solve it. And this one involves quite a bit of algebra, okay? I'll give you a hint here. In order to do this one, you're going to need to use the quadratic formula. Remember the quadratic formula? It says if you have something of the form ax squared plus bx plus c is equal to 0, then the solution of that is x is equal to minus b plus or minus the square root of b squared minus 4ac all divided by 2a. Okay, so this involves a lot of algebra. Whenever you get into upper level math courses, at that point you need to assume that you know the stuff that you've learned in the earlier courses. So I'm assuming you know your calculus. I'm also assuming that you know your algebra. Okay, but anyway, you're going to need that. So let you finish that. Let's see, how are we doing? So we might as well go on. So now, after this, we now go on to an even more interesting problem. Now, suppose we still have all this stuff. Let's see, I'll leave this up here for now. But now, assume that you're in a river where instead of having a uniform current, which is always the same, like 2 miles an hour going that way, now suppose that the current depends on the place on the river, which would typically be the case, right? If you have a river, maybe the river looks like this, or maybe other streams run into the river, so that as you go down the river, the velocity keeps getting faster and faster as you go, right? If you watch the velocity right here, maybe it's going at 2 miles an hour, maybe right here because it's narrowed or because other rivers have flown into it, maybe it's going at 4 miles an hour, maybe here it's going at 6 miles an hour. So the velocity is going to depend on where you are along that river. If x is the position along that river, then V sub c is the velocity of the current at that point along the river. Okay, so it's going to change as you go. So let's look at this one. This is Roman numeral number 5 now. Okay, so if you look at that, you'll see, and again, I'm kind of giving you the kind of an augmentation of what's already in the textbook, but the energy, notice, is going to be the force times the distance, same as before. And the force is going to be the same thing as before. At every point, if V, I should be really clear here, V is the speed through the water. That's the speed through the water. Okay? So the force is going to be proportional to the speed through the water. So that's the same as before. And now, the effective distance that you go, it's not going to be P again, because you're going against a current. The effective distance is going to be your speed through the water times the amount of time that you're traveling, right? Same as before. It's the speed through the water. That's what you had right there. See that? That was your speed through the water times the amount of time that it takes. And as before, we're going to have to come up with a formula for the time it takes. Okay? It won't be quite like this, because this was pretty simple. This is when V sub c was a constant value. Now it's variable. Okay? So we need to figure out what this is going to be. Okay? So what can we do? Well, continue on here. It says the time it takes can be found through a simple algebraic method. Number 1, I say express. So here, right here, is your x-axis. This is the distance along the river. And so right here is point x. And so dx dt, that's the rate at which x, this distance right here, it's the rate at which x is changing. Let me make sure that you're still with me here. Okay, very good. It's the rate at which, it's the velocity. It's the rate at which this distance up the river is changing. So dx dt, that's the rate at which this distance is changing, that position is changing. Do you agree that that is going to be the velocity of the boat, same as before, the velocity of the boat through the water, that's V, subtract the velocity of the current, as before. This is the velocity along the bank. So x is the distance along the bank. So there's your velocity along the bank is equal to the velocity through the water minus the speed of the current. But now, instead of being just a constant, that's going to depend on the value of x. It's going to depend on what x is. As we say, it changes as x changes. So we need to figure out how much time is it going to take to get from here to here, given that this is our expression. And as soon as you see that, hopefully you think, that is a differential equation. And that is not only a differential equation, it's a separable differential equation. Because look, I can write dx divided by v minus vcx is equal to dt. Agreed? And so we've separated it. And now, if we want to go this whole distance from there to there, that means I want x to go from 0 to p. And if x goes from 0 to p, then that's the total amount of time it takes. So it's going to start at time 0, and when you're right there, and by the time you finish, we're calling that time t. T is the total amount of time it takes to get there. So here is a differential equation that we have, which models this situation where you have a variable current. Isn't that cool? And so now, I think I can get rid of all this stuff for the time being anyway. And so if I evaluate both of these sides, this is just going to be antiderivative of 1 is just t. Evaluate t from 0 to capital T. Stick a capital T in there, you're going to get capital T. Put a 0 in there, you're going to get 0. And so you're going to get capital T is equal to the integral from 0 to p of 1 dx all divided by v minus v, like that. There's the amount of time. So there's the amount of time it takes. Now, that's a nice expression, but unless we know what this is, we can't go any farther than that. So at this point, notice in problem on page 37, number 2, it says, suppose you are going upstream in a current where VC is equal to some constant times the position P. So in other words, on the position X. So as you go down this river, the current just keeps getting faster and faster and faster as you go. Okay, right here the current is 0. By the time you get to P, it's going to be alpha times P, and it's just going to keep going faster and faster as you go. So now we can go ahead and put in alpha X right there, and we have that expression. So this is as far as I'm going to take you on this one. I give you directions for how to finish it now, but now the next step to do is to find the antiderivative of that. Notice that X is your variable. See that? X is your variable. This is just a constant. So you can use substitution or just think about it with you're going to end up with a logarithm, and I kind of give you hints as to what that's going to all look like, and you stick in your limits and all that sort of thing, and you go from there. So there's a lot of interesting stuff to do yet, but there's kind of the meat of the problem. And as always, you can if you're taking this course from me, then you can give me a holler and I'll give you some help. But those of you that are just working from Australia or Germany or whatever, you're on your own. See if you can figure it out. Okay, very good.